morning. Okay, so we'll finish the impulse function today, and then we'll look at relationship between unit step function and impulse function. Okay. And after that, I think we still have time, and we'll look at another topic called impulse response of a linear time invariant system. Okay. Just a quick review of what impulse function is. This is a definition of impulse function. Okay. So definition, as I mentioned, definition is something we don't argue. Okay, so this is something everybody agrees upon. Basically, delta t is 0 when t is not 0, but delta t is infinite when it's 0. And if you integrate delta t, the area underneath the delta t is actually 1. To indicate delta t, you can just simply draw an impulse at t equal to 0 to represent this delta t. But as a question asked at the end of the previous lecture, I think, to help you understanding delta t, it might actually helpful to understand delta t instead of just a straight arrow. You actually try to understand it as we did in the previous lecture. Basically, try to understand it as a rectangle, symmetric rectangle with a unit area 1. Okay, the unit area 1 under this rectangle, and this rectangle can be infinitely tall as epsilon goes to 0, right? But doesn't matter how tall it is, the area underneath that rectangle is always 1. Okay, so instead of visualize delta t as just a straight arrow like this, if you can visualize delta t as if like this, it probably can help your brain to accept a little more, make it a little more acceptable. Okay. And we have also derived a couple of one property called sampling property. The sampling property basically says this. We show the proof of it in the previous lecture. So if you multiply f of t with an impulse function delta t, and then you integrate about this function, the multiplication from negative infinite to positive infinite. Yes. No, well, unless you put a negative sign in front of it. Yeah, if you put a negative sign in front of it, it'll go down. Yeah. But the delta t itself, by definition, it's an impulse going up. Yeah. Good. And this one here gives us f of 0. Okay. So it's as if it gives you the sample value of f of t at t equal to 0, right? That's what they call the sampling. Okay. If you multiply, instead of a delta t, multiply with delta t minus capital T, so a shifted impulse, okay, a shifted impulse, then it will give you f of capital T. Right? So the sample value at t equal to capital T. So you can take a look at the proof in the lecture notes. A very simple proof. Okay. And sometimes these properties is also called a shifting property. Okay. Just like the word itself, shifting, right? what's remained out of this operation is just one sample value. Okay. So before we look at an example here, maybe I'll ask you a quick question. Where is delta capital T minus T? So if I ask you where is delta T minus capital T, and you can immediately tell me, you will see this is just shifting delta T to the right by a capital T amount of length, right? Yeah. So this one will be at this. But what about this? Where would this delta capital T minus T be? So yeah, this is a reflected of this, right? But what's the relationship between these two? If you recall, this is basically a property I mentioned. You try to visualize your function of this, right? This is an even function. So if I start, let's see, if I start with this, okay? Let's start not with this. If I start with this one, okay, and then I'll take a negative sign out. Okay. Because of the even function, so this actually will become this. Okay. So basically, delta capital T minus T is the same as delta T minus capital T, because of the even property. So you can draw the same thing as this. Okay. Yeah. Okay, let's take a look at an example here regarding this sampling property, okay, or sifting property. Okay. Now this would be probably very quick calculations, or even like a multiple choice or whatever, right? In an exam to ask you to calculate it. It shouldn't take you much more time. It's less than 1 minute. You should be able to finish this kind of question. Okay. Calculate this integral at here, and that's exactly the sampling property number 1 at here. Okay. So what you can do is you can just simply use the results because this is delta t. So we're looking at is the value. This is your f of t here. This is your f of t. We're looking at the value of f of t at t equal to 0. Okay. Any questions so far? It's all good? Okay. So then t equal to 0 substituted, you got 1, right? Yeah. Let's take a look at a slightly different one here. Okay. So let's see if you have a cosine pi t over 4 times a shifted impulse function, delta t minus 2. So you basically will apply the second shifting property formula here, because this shifting by 2, then you let t equal to 2, right? So that becomes pi 2 over 4, so pi over 4 cosine 90 degree, which is 0. Okay, so that's the idea. It doesn't matter how complicated this function at here is. All you need to do is substitute, look at what which impulse function you're multiplying with. Okay. Okay, before we move on, let's take a look at one more example. Let's look at what will be the convolution between f of t and delta t. Okay. Convolution of this. You should jog your mind that, you know, basically we did a convolution of f of t and u of t, right? Yeah. If you recall that convolution end up with what? End up with just the integrand f of t there. Okay, so basically give you the area underneath f of t. So let's take a look at what will be the convolution between these two, okay? F and the impulse function. First, plug in the formula. Okay. But before I plug in the limit set it here, okay? Yeah, and the typical limit is 0 to t, okay, which is what we have done. But when I plug in the 0 to t, I think if you recall that there is a assumption, which is that both of the functions, right, we're convoluting are causal signals. Okay, yeah. But convolution really doesn't restrict to causal. You can also basically convolute two general function, maybe non-causal. Basically, the function can be from negative infinite to positive. So there's something when t is less than 0. Okay. So in this case here, okay, if I don't say this f of t is a causal signal, okay. So it could be non-causal. The integral limits, okay, which will become just negative infinite to positive infinite. Okay, so I'll show you this one here using this special case from negative infinite to positive infinite. So positive negative infinite to infinite. This is for general type of function f of t. Okay. So it could be non-causal basically. Alright, so let's proceed from here, and we'll make use of a property for delta function again. Make use of the even function property. So we will take negative sign out and become delta negative tau minus small t. And because the even property, so we can get rid of the negative sign. There. Okay. Okay. And once we're at this step, here, so we have to be very clear as to the perspective now. This is integral with a dummy variable tau tau tau, right? So when you're integrating with respect to the dummy variable tau, and then you're treating the t now as what? As constant. So if I only focus on the multiplication at here, even though the t is actually the variable, right, the original variable, but in this case, these two multiplication, you are actually considering the tau as the variable and then t as the constant. Okay, so this multiplication basically give you which one? F of t here, right? Remember when you have any function time the impulse function, okay, because the nature impulse function, it only exists at that single moment. In this case, only exists at the moment when tau equal to t. So you don't have to worry about anywhere else. That's why you can replace this tau with t in here. Okay? Yeah. And because you're integrating with respect to tau, so this f of t is actually becoming a constant as a whole, right? So you can move this term out of this integrand here. Okay. And finally, you're only left with integral of this shifted impulse function. And you're integrating from negative infinite to positive infinite. So what do you think this one should equal to? 1. Excellent, right? Area underneath that impulse function is always 1. Because it's negative infinite to positive infinite, it definitely will cover that small triangle, right? The small rectangle. Okay? Yeah. So in total, you get f of t at here. So basically means when you are convoluting any function with impulse function delta t, you get f of t. You get back this function f of t, like nothing happens, right? Yeah. Similarly, you can prove this. If you're convolute, yes.
I want to ask, how do you change from f tau to ft?
From here to here?
Yeah.
Now, because this is tau here is the variable. Remember, if I have f of t times delta t, what do we get? F of 0 times delta t, right? Yeah. But of course here, let's see if I change to tau. This is variable tau here. So that will be f of 0 times delta tau, right? Yeah. And then if I change this to this is tau, sorry. If I change this from delta tau to delta tau minus small t, so you consider this small t as a constant, right? Yeah. So shifted one. So that's why it becomes f of small t times delta tau minus t. Okay? Yeah. Good. Okay, so I want you to try this. If you convolute a function f of t with a shifted impulse function, you should get this. Okay, you'll get a shifted function f of t. All right, so that's a property here. You don't have to memorize the procedures, but I think just like this one here, right? The two special convolution between a generic function f and the special function, unit step function, and the impulse function. Okay, so that's it for impulse function. Before we move on at here, let's take a look at the relationship between unit step function u of t and impulse function delta t. So let's take a look at this relationship. I'll give you the relationship, but it's not going to be a very rigorous proof at here. Okay, the results, the conclusion will hold, but there's not going to be a rigorous proof. So first of all, let's take a look at the u of t. This is a u of t at here. So u of t goes 0, 0, 0, and then jump to 1, right, and then goes all the way to the right. Okay. So let's observe this u of t at here. If I'm going to ask you to take what will be the derivative of this u of t, right? So before we give you the results here, let's consider the way we conduct the derivative. Okay? Yeah. Derivative means what? It means the slope of the curve. Okay. So slope of this curve. And you look at this curve, this is the red one, is the curve here. So if I go starting from this area, this is a flat, right? That means the slope must be 0. And this portion is also flat. That means the slope must be 0. It just at here, it's not flat, it's straight up. Straight up means slope must be infinite. So this derivative essentially gives you 0 when t is not 0. And when t is 0, you get infinite. And that's actually what? The impulse function, delta t. Okay. So I said this is not actually rigorous proof. Okay. This actually seems simple. Honestly, I didn't dig too much deep into it, but if you dig deep, there's mathematicians will take much more pages to actually prove this. Okay, yeah, that's none of our business, but that's enough for us. Okay, yeah. Now reverse, okay, vice versa. If we're going to, for example, integrate a delta t. Okay, instead of t, let's call it tau here. Okay. If we're going to integrate this function, then we should get actually u of t. Okay. That's vice versa. So this is the connection between these two. Right? So if you integrate this, you get back this. Good? Okay. How about now? If now we understand this now, if we do this, let's see, if we have a derivative, okay, taking derivative of 2ut over dt. So basically means instead of this is 1, right? It goes up one more notch, okay, up to 2. Okay, and then you take a derivative of d2ut over dt. So according to the definition, mathematically, if du of t is delta t, then the 2 here give us what? So 2 times delta t. Okay. Yeah. And how about this one? So if I have a d2 u minus t here. Okay. So shifted unit step function. Basically, shift by 1. So here is 2. Right, 2 times u of t minus 1. Alright? Then the derivative of this should give us 2 times, so you should have an impulse at this location, 2 times delta t minus 1. So the impulse will be at this location. And 2 times delta t, or 2 times delta t minus 1, as I reiterated at the beginning of the lecture, when you consider delta t, you should visualize, okay, I have actually a rectangular box whose area underneath the box is 1, right? If I have a 2 times delta t, then you should also visualize, okay, there's an impulse, okay, but the area underneath the 2 times delta t must be 2. Right? The box just skewed up a little bit for the area. Okay. Okay, so that is the connection between the impulse function and unit step function. Now, interestingly, sometimes I'll show you an example here. So let's say I have a function x of t. Okay, this function x of t looks like this. If you have a piecewise function x of t, okay, goes like that. the next question is, what will be the derivative of this function x of t with respect to t? Okay? Yeah. So let's start from the left side here. This portion is all flat 0, so as you go, the slope must be 0, right? And at this -1 location, there's a jump. So the slope at this location will be infinite, but that's what we call delta t. And the magnitude here, this is 1, right? This is 1 here. So at -1, you will have a delta t at here. Okay. Then from here up to t equal to 1, it's a flat again. So basically it go back to a slope of 0. So this is 1 here. So what happened at the t equal to 1 here? Then it goes all the way down. It's still vertical, right? So basically it should become, instead of positive infinite, it should become negative infinite. But instead of calling it negative delta t, but this is at which location? At t equal to 1 location, right? At t equal to 1 location. So at t equal to 1 location, you have an impulse delta t minus 1. That's this location. And it's negative. However, if you look at the amount of jump is from where to where? From 1 to -1. So the magnitude of the jump is -2, right? Or 2. Okay? So how do we do that? We have -2 times delta t minus 1. Okay? Yeah. And then back to t equal to 2. There's one more jump here. Right? It's delta t minus 2 at here. So that's the nature of the derivative of this original black box here. Right? All good? This is visually, right, to show you. If you want, you can also actually mathematically to derive. So this is x of t. I can express x of t with unit step function. So here's what what would that be? This box right here, the top box, is basically u of t plus 1 minus u of t plus minus 1. The bottom box right here is u of t minus 1 minus u of t minus 2, and then put a negative sign in front of it. So x of t basically can be constructed through 1, 2, 3, 4 unit step functions. And you can simplify this, which becomes right? Yeah. And now you can calculate the derivative. As we said, derivative of sorry, this is wrong here, right? See, this is exactly, there we go. Okay? Yeah, delta t plus 1. So the derivative first one give you delta t plus 1. The second one give you delta t minus 1. The last one give you delta t plus 2. Okay. So that's more mathematical way of getting it. All right. Any questions so far? Yeah. I know this is the part. Okay. According to my experience, okay, I know some at this stage, especially second year, they seem to be very abstract, especially those symbols, right? Never seen this before. Yeah. Okay. If you don't have any question, then I'll move on to a new topic. Okay. So this is what we write at the beginning here. Let's look at the so-called impulse response of LTI systems. Impulse response of LTI system. As you're going to see, we actually will get the convolution involved again. Okay. So first of all, let's understand what does response mean, right, for a system, and then let's understand what's impulse response of this LTI system. Okay. So first, let's understand response. Response means what? Means if I have a system at here, and we represent the system using an operator M, then we give the system input x of t. So we feed the system with certain type of input. The certain type of input can be as simple as a constant, or as complicated as a sine, cosine, or a combination, right? Or as later we're going to see, it could be even just an impulse signal. Okay? Yeah. Basically any time function. Then the system must produce an output, right? So this is output at here, y of t. The output, we can also call it basically response of the system. Okay, that is the response of the system. Okay, so now let's consider a special case now. Okay, let's consider a special case. Instead of a general input x of t, this time we will give the input as delta t. So we feed the impulse response, we feed the impulse signal into the system. Okay. Now this is a very special case. Okay. When you feed impulse signal into the system, the corresponding output y of t is called impulse response. And we use a special symbol. Instead of a y of t, we use h of t, okay, to represent this special response, impulse response. So basically h of t equal to m delta of t. When your input is delta t, your output is called impulse response. Okay, you can repeat this sentence yourself a little bit here, because that's actually basically the definition of impulse response. Impulse response means when input the system is impulse. That's it. Okay, whatever the output is called impulse response. And then I actually can present you with a very, very important theorem, okay, for LTI system. Okay. So let's look at a theorem at here. This is very important ones here. For a LTI system, okay, with impulse response h of t. Okay, so that basically means you have an LTI system and you have obtained the impulse response. And how do you obtain that? You have feed the impulse to the system, and you grab the output. That's the impulse response. Okay, that's how you obtain the impulse response. And I'll see a little bit words about how do you get impulse input. Okay, that's another different things. Okay. Suppose you have an LTI system with impulse response. Okay. And now you change the system input to different ones. So now the input, it becomes a general input x of t. So not an impulse anymore, okay? Yeah, that could be still an impulse, but a general, just x of t. Could be anything. So now the input becomes x of t. Then we have the following basically property. The following property here. The property says this. So here is an LTI system, and this is the this is the input x of t, right? Input x of t. The output, right, is what we care about. Okay. Right, so we wonder what will be the output y of t. And because this is an LTI system, and also because you have this impulse response h of t, that in this case, you don't even have to do any experiment. Your output here will be a convolution between your current input and the impulse response. Okay? Yeah, so we're twisting words that are here, right? Yeah. So let's repeat this, okay, but let it sink in for a little bit here. Okay. First thing, as always, you know, when you see a new thing, first thing to understand is what does each one of the symbol here represent. Okay. Make sure you're absolutely clear which each one of the symbols that are here. In this case, this is my output. This is the input. You're dealing with the LTI system, and you have the impulse response. Then you look at the result. The result says the output corresponding to the input x of t is actually x of t convolutes h of t. Okay, that's basically what this theorem tells you here. Okay. It's a very powerful theorem. Why is it powerful? Can you think of it? So let's say if you have a black box representing a system, right? Or the system could be anything. Okay? The system could be anything here. Let's say your objective is to understand the system. Understand the system basically means you will try to understand the dynamics of the system, the characteristic system. Once you understand the system, you can deal with it, right, any way you want. Okay. But how would you understand a system? Like, for example, how would you understand a person, right? If I have a stranger in front of me and I want to understand the person better, like in the interview, you got to talk to him, right? When you're talking, you ask all different kind of questions. All of the questions basically are what? Inputs. And then the person responds. The response is basically the outputs. So you try to get as many type of responses as possible back from the person. And then you understand exactly, is it a team player? Is the person best fit into the working environment, right? Okay. So basically you're trying to inject different kind of inputs to the system. Try to get as much as possible output as back. And then looking at the output, then you understand the system. Okay? Yeah. So that's a very tedious way of doing it. But you have to do it, because otherwise how do you understand the system? Okay? Yeah. But now if you look at this theorem, now this theorem actually gives you a shortcut. Instead of asking so many different questions, maybe, just maybe, right? Maybe I can just ask one question. That one question is what type of input? impulse inputs. I don't know what that question is, okay? But if that question is actually an impulse input, once you ask the question, you get the answer. That answer is called impulse response. And once I get the impulse response, okay, you can go now, right? And then I will go back to my computer to do this convolution. I will know exactly what your response would be corresponding to other type of questions. You got it? Right? That's what this theorem is so powerful right here. Okay? And that's actually the ideal situation, right? The ideal situation. And this works only for LTI system. So the bottom line is, you strive to find the impulse response of a certain system. Once you find it, then you save yourself tons of work. You can just simply plug in this the current input, convolute the impulse response, and you get the system output corresponding to this input. And it's like doing experiment too. If I have a system and I want to test the system, okay? So I'm going to borrow maybe an oscilloscope and signal generator, okay? And the signal generator will give me different kind of signals, okay? Maybe sinusoidal, maybe different things, okay? So then I plug in this sinusoidal with different frequency into the system and I'll observe system output. As a matter of fact, that is one type of things. We call that frequency response, okay? Yeah. However, the other way of doing is, I will plug the system with a certain impulse signal. Once I get the impulse response, and I don't need to care about any other different inputs anymore. I can just convolute the input, that type of input with the impulse response. Okay? So that's why this is a powerful one here. Right? So the question, of course, here is there are a number of questions. First of all, there's actually a proof with it. There's a proof associated with this theorem right here. Okay? It's not a long proof. Maybe I should just show you the proof right here. Okay? Yeah. And the second question about after the proof will say is, how would you produce a impulse input to the system? Right? That's actually a difficult question to answer. Okay. So proof of this one here is this. Okay. This is the current situation, right? So you have an input to the system, and you're interested in finding out the output of the system. Okay. Now I'm going to manipulate this x of t, okay, and but not changing it. And this is a property we'll make use of that we just find it out. If I convolute this x of t with delta t, okay, as I have just shown you, any function convoluting impulse function will actually give you back this x of t, right? So this is not changing anything, still x of t. But then I can write down the formula, right? Using convolution formula, write down this convolution in here. Okay. So I'm going to assuming non-causal signal here, so from negative infinite to positive infinite. So we have x of tau delta t minus tau d tau. Okay. Right, that's pure definition of convolution between these two functions. Okay. Now remember we're dealing with is LTI system, linear time invariant system, right? Yeah. So integral, right? First of all, integral, as I always said, you consider integral basically summations, right? Summations of this is a dummy variable tau, so maybe x of negative phi times this times something times delta t plus x of 10, right? So basically multiplication, summations, right? Summations of multiple entry points. Okay. Now, if you look at this one right here, okay, if you look at this one right here, for this integral, the dummy variable is tau, but where we're looking at the original one is actually in terms of it's the t, right? It's the t. So basically this x of tau at here, okay? If you recall that mc times x of t equal to what? C times mx of t, right? Yeah. So this c is a constant versus this x of t. And then if I look at this bracket here, this one basically I consider it as a constant now, right? Because this is a t at here, okay? So this is a constant. How many constants? There's so many. There's integral. There's like an infinite number of constants at here, okay? Yeah. So if it's constant, I will apply this homogeneous property. You can take the constant out of the bracket here, right? So this x of tau, you can take it out of this here. This m can move into this bracket. So basically, it becomes m delta t minus tau and d tau. Okay, so that's linearity from here, right? This is making use of the linearity at here. It's not a very obvious linearity, but it is linearity. If you expand this integral and you also consider this one as a constant, there's a lot of constants at here, okay? And a lot of additions. So there are two additive and yes.
So you consider the x of tau to be a constant.
Yeah.
Even though you're still integrating with respect to tau.
Yeah.
Okay.
Right. Because the m operates on the t, right? Yeah. So now I have this, okay, and then we just have to worry about this term now, right? What about this term? Okay. And this term means what? Means you have an impulse input to the system, right? This is impulse input to the system. It's a shifted impulse, of course. Okay, it's a shifted impulse. Shifted by this much tau. So delta t produce impulse response h of t. Then delta t minus tau, because the system is time invariant, then delta t minus tau should produce what? Exactly, right? That's the linear, that's the time invariant property here. So this portion will be the time invariance. So this one will give us ht minus tau here. Okay, so your original manipulation from here to here end up with this guy. And this is exactly, basically, according to the convolution formula, this is x of t convolute h of t. Okay. So that's a simple proof. Okay. There's a little bit of detail behind it, okay, but you can, accept and you don't have to understand completely from now. But of course, the conclusion, right, has to be very firmly believing in it. Okay. How good? Okay. Okay. So now to answer actually. A couple questions before we move on to next lecture Friday. I think I asked the question basically, what would be a physical example of impulse input? Okay, so we all know that impulse input is delta t. So delta t, basically you have an impulse at here. Mathematically, it's a very high, it's an infinite, right? It's infinite here. So if I want to create an impulse input in reality, what are the examples you can think of? What would be an example of an impulse like this? Or maybe first of all, can you even create a thing like this in reality? Can you? Infinite. You can't, right? But then can you, maybe the guy, can you create something similar to this as like an impulse input? So what would be an example? You learn actually similar in dynamics. So for example, if you threw a ball, right, to the wall or to the ground, it bounced back right away, right? That moment of the impact is actually kind of impulse. If you use a hammer and hammering this drum, but you don't hammer it and let it stay on it, you just touch it and then let it go. So that momentarily a touch or hammering the contact is an impulse. Okay? So that's basically the type of input you can generate in reality as close as possible to an impulse function like this. Okay? Yeah. I'll give you an example in the next lecture how to apply this, okay, in LTI system.